Hi, this is Layla Laney, and this is Lab 3 for Magnetic Field of a Bar Magnet. In this lab, we will be determining the distance dependence of on and off axis magnetic fields using equations derived from the Boule-Savart law. Then we will compare those results to the measurements we take for the distance dependence of the magnetic field due to a small bar magnet. Here are the results that I got using the equations we derived from the Boule-Savart law. So our magnetic moment is 24.58 amperes meters squared. Our n is negative 1.8842, and k is 4.916 e to the negative 6. Okay, so first let's look at the magnetic field of like a bar magnet. So the magnetic field of a bar magnet has the arrows pointing away from the north side, pointing down on the sides, and then pointing towards the south. And it just kind of loops around. And this phenomenon can also be seen like in a ring and even in other forms where like in a ring it doesn't have a north and a south pole, but it does have each side that acts like the north and the south, where we have the arrows coming out, wrapping around, and then going back in. For our experimental procedure, the system is the bar magnet and the surrounding is everything else. First, note that before we measure the magnetic field of a bar magnet, we have to account for the Earth's magnetic field that is also present. We can superimpose the two magnetic fields to find the net. This is why in the experiment we place the bar magnet on the edge of the ruler that is perpendicular to our smartphone that we align with the Earth's magnetic field. After aligning the phone to Earth's north and south axis, we slide the phone up and down and then across to find the magnetometer sensor. Then we record the distance the phone moved to get the x component of the magnetic field of 20, 70, 120, and then so on. Then we slide the phone across and then up the rulers to find the distance d perp, where the net magnetic field is 100. We input all of this into our spreadsheet to calculate the net magnetic field. So as you can see here, this is all the data that I compiled into the spreadsheet, and then this is the graph that we got. So as you can see, like looking at our equation of the line, it's negative 1.8842x minus 12.223. Now here are my calculations to find n, k, and then the magnetic moment. So for n, we took that equation that we got from the graph, and just by looking at it, we know that it's in like y equals mx plus b. So the slope of that would be what n is, which is what we got, negative 1.8842. Then for k is the y-intercept. So we just picked the natural log so that we could like isolate k, and that's how we got that number. And then to find the magnetic moment, we set the equation of like the magnetic field of a bar magnet equal to krn, and then we isolated the magnetic moment and plugged everything in and got that number. So, key observations from the experiment, I did notice that basically as a magnetometer was closer to the magnet, the component of the magnetic field increased, and as it moved far away, it approached zero. So for my globe script, you can see that I showed how to calculate the dipole. I scaled the arrows to calculate the average dipole perpendicular and created the arrows to represent the perpendicular and on-axis magnetic field lines. And they are like blue and orange, you can see them here. Then I calculated the magnetic field at 45 degrees. Now for our discussion. One error that could have occurred in our experiment is calibrating the magnetometer incorrectly. That would have caused like interference. For our what if questions, the first one is, what if we hadn't oriented our experiment to compensate for magnetic north and had instead laid out our meter stick at some intermediate angle with respect to the Earth's magnetic field? So this would like change all of our numbers. You know, in the beginning, the whole purpose was to find the net magnetic field. In order to do that, the Earth's magnetic field had to be perpendicular to the magnetic field of the bar magnet. So that would just change all of our measurements. And then what if we were to stick two identical magnets together end to end and run the experiment again? How would the measurements differ? So overall, the magnetic field would be smaller because like the when they're stuck together, like the magnetic fields coming in and looping around is like it's not equal. So that would kind of change our measurements to end up with like a smaller net magnetic field.